Let's look at the strange formula for entropy that thermodynamicists use to calculate the entropy of a system. Okay, we like to popularize entropy as an amount of disorder. Okay, the second law of thermodynamics states that natural processes tend to cause a net increase of entropy. Um, it can either be no change at all or it can increase. Okay? And almost all natural processes actually cause some increase of entropy, which is disorder, right? Another way to say the second law is to say that heat will flow from hot to cold. Okay, and I'm going to use that. Okay, the idea of heat flowing from hot to cold to show you that when heat does flow from hot to cold, that it does cause a net increase of entropy. We can work this out. So in that way, this works. Okay, um, but it's really it's sort of an abstract concept, and it's hard to wrap your mind around this. Okay, so let's look at some examples here, and I think this will help us. Okay, so let's look at this piece of iron placed in a cup of water. They come to equilibrium at 31 degrees Celsius. Okay, and so here's this cup of water. Okay. And there we go. And we stick this little piece of iron in there, right? And heat is going to flow out of the iron, okay, and into the water. So the water will have a positive Q. Is a positive Q, and the iron is going to have a negative Q. The heat is going to flow out of the iron, okay? And our change in entropy and then let's figure out what the Q is in this case, okay? So Q is mc delta T for the iron. So that is 0.035 kilograms times 450 joules per kilogram degrees Celsius. And then it changes by, let's see, it's at 35 and it goes to 31. So that's 4 degrees. Minus 4 degrees Celsius. So this is Q for the iron, right? Okay, so let's figure that out. 0.035 times 450 times negative 4. And I get that for the iron, Q is negative 63 joules. It loses 63 joules of heat, right? So let's figure out for the iron, okay, what's its change of entropy, right? So change in entropy is the heat flow, and that's going to be our negative 63. That's easy, right? Why there's a delta Q here when all the other times Q means delta Q, you know, there it is, right? And that's because really this is a calculus expression, and so we're tiptoeing around that notion. Now here's the problem, and this is why it says estimate, okay? Is that we need to integrate this and figure out differentially all the little changes, right? Because this iron goes from 35 to 31, right? Now, on the average, it's 33 degrees, right? So the iron is, the average temperature is going to be 33 degrees Celsius, okay? That's why it's an estimate. Really what you have to do is you have to do some sort of an integral. You have to use calculus here because it's constantly changing from 35 down to 31. Okay, I'm just simply going to use the fact that its average is 33, and we're going to get an estimate of this, right? So for temperature, when we plug this in, we'll go minus 63 over the average temperature of the iron, right? This is not really, you know, if the temperature change is small, it's pretty close. If it's a big temperature change, it doesn't work so well. Okay. So really, you know, we really can't use this formula, but that's okay. Let's use it anyway. Okay. Okay. So here we go. So negative 63 divided by parentheses 273.15 plus 33, right parenthesis. And I get that the change is negative 0.20578. And our units are joules per Kelvin for entropy. Okay. Now let's do for the water. Okay, for the water it's the same thing, right? Only it's Q is plus. The water gains the heat that the iron lost. Okay, so we go positive 63 joules. Now the average temperature of the water went from 30 to 31, so the average temperature is 30.5. Okay, so I'm going to do 273.15. Did I say that temperature must be kelvins? I hope you understand that when T is ever alone in an equation like that, it's not a change in temperature, it's got to be absolute. All right, so 63 divided by parentheses 273.15 plus 30.5. And I get that is positive 0.2074757. Now, notice that the water had a lower, the cooler reservoir had a lower temperature on average. So therefore, since you're dividing by temperature, the change in entropy for the water was higher than the change in entropy for the iron. So it's not true that parts of a system have to increase their entropy. This part actually decreased its entropy. The second law just simply states that when heat flows from hot to cold, okay, the entropy will increase. And in fact, it did, right? This is a bigger positive change than this thing's negative change. Creationists like to say that life could not evolve because life is a decrease of entropy. It's an organization, right? And when you organize things like make cells and stuff like that, that's a decrease of entropy. And the second law states it can't happen. And in fact, the second law states no such thing. You can have local decreases of entropy, just that the world itself has a net increase. Somewhere else there was a net increase, right? But anyway, you can take a look at this. And then what is our net change? Well, we have to subtract, we have to add these two together, right? So let's go that guy plus negative 0.20578.147. And I get that if I add these guys together, this guy and this guy, right? If I add those together, I get this. I get 0.00169 joules per Kelvin, and that's a positive change in entropy. There we go. Okay, so in short, when you're doing this thing, right, sometimes you have to calculate what the Q is, right? And then when you divide by the temperature, it's got to be absolute temperature. And if the temperature changes, you're always estimating. Okay, the real calculation requires calculus. And then just use the average. That seems to be the consensus. Okay. Now let me just do an example of one where we actually don't have to average. Okay. Check this one out, right? Let's throw a nice ice cube into a pool. Okay. Let's assume that a 68-gram ice cube does not change the temperature of the pool. Okay. I think that's reasonably true, right? Let's also say that the ice cube, until it melts, is at 0 Celsius, right? And that also is true, right? So let's figure out the change in entropy of the ice cube, right? Okay, so the Q for the ice cube is ml, right, is 0.068 kilograms times 3.33, because this is a phase change, right, joules per kilogram. So 0.068 times 3.33 E5. That's 22,644 joules. Okay. So, and for the ice, it gains that heat, right? For the ice, the change in entropy is Q over the absolute temperature, right? Okay. In this case, it gains that heat, 22,644 joules, and for the ice it's at 273.15 kelvins. Okay, so divided by 273.15 and I get 82.899. And that's joules per Kelvin, right? So that's a positive change of entropy. And if you think about that, think about an ice cube, right? A solid is very orderly. It's all these little crystals. They're all in a beautiful order. In fact, if it's a snowflake, imagine all that order, right? You can kind of imagine a cube here or something like that. Okay, very, very orderly. Actually, it's not cubic, though. It's crazily hexagonal or something like that. Okay, but it's very, very orderly. And then as it becomes a liquid, it's a phase change causes a tremendous change of entropy. That's because when it's a liquid, even though the particles are still in contact with each other, they're moving all around, and it's all very messy, very, very disorderly. Okay. So phase changes represent large changes of energy and therefore also entropy. Okay, now the pool. Let's assume that the pool's temperature does not change, that it stays at 18. And this is a relatively exact approximation. It's still an approximation. Okay, so for the pool, our change in entropy is delta Q, right, over the temperature. So the pool actually cools down. So it loses 22,644 joules. But because it's so big, its temperature doesn't really change much. Right? So we're just going to say that it's 273.15 plus 18. And this is, by the way, more or less an exact calculation. So phase changes like this we're not really estimating, we're calculating. Okay, so here we go. I'm going to store that answer in A. Okay, so now I'm going to go negative 22,644 divided by parentheses 273.15 plus 18. Hopefully that's an appropriate pool temperature. Okay, and I'm getting that is negative 77.774 joules per Kelvin. Okay, and I'm going to store that in B. Okay, notice that because the pool is at a higher temperature than the ice cube, okay, that its negative change of entropy is smaller in magnitude than the positive change in entropy of the ice. This is always true when heat flows from hot to cold. Okay, the thing that gains the heat is always at a lower temperature and therefore has a higher change in entropy. Then the thing that loses heat is always at a higher temperature and therefore has a smaller change in entropy. You always gain entropy when heat flows from hot to cold. Okay, and let's take a moment here to think about why that is. But first, let's answer the final question. What is the net change in entropy? Okay, it doesn't ask for that, but let's get the answer, right? The net change is just simply alpha A plus alpha B. So the net change is positive 5.13 joules per Kelvin. Okay, that's the net change. This is the ice. This is the pool. Okay, now let's think about why heat flowing from hot to cold is a change in entropy. Let's wrap our mind around that. Okay, let's just imagine we have a couple cups of water here. Hot water. Okay, this is very orderly. We know, where's our hot water? Well, our hot water's here, okay? And then here we have cold water, right? We have cold water, right? Whoops. If that's cold and hot water, if we pour that all together in some larger vessel, okay, we lose the information about where the hot water is and where the cold water is, okay? And so when we pour those together, it's just sort of lukewarm. It's tepid, as it were, right? Where's the hot particles? I don't know. They're all mixed up, okay? Where are the cold particles? Well, they're all mixed up there, okay? They're just mixed up in there. It's all mixed together. It's a bit like if we, if we took a cylinder and filled it with layers of salt and then pepper and then salt and then pepper and salt and pepper. If we didn't shake the container, we'd know exactly where the salt and the pepper was. It's not mixed up, but if we shake it and mix it, it all mixes together and we increase the entropy, okay? So heat flowing from hot to cold, basically we lose the information about where the hot and the cold particles are, right? In fact, at some level, when they talk about entropy, it's a crazy, crazy abstract thing, but it has to do with how much information we have about a system as related to its entropy, which of course, brings up the interesting question of if we mix hot and cold water together and throw it into a black hole, it leaves this universe never to come back again. And so, what happened to that increase of entropy? Anyway, I'll let Stephen Hawking explain that to you.